This chapter 7 is essentially about entropy, and the specific things that we'll cover in this chapter would be clauses inequality. We'll uh, define the clauses inequality, and based on this clauses inequality, we'll define the new property which is called entropy. And it is essential to quantify uh, we'll try to quantify the second law effects. We'll also establish the increase of entropy principle. Uh, Furthermore, we'll be looking into the entropy changes that takes place for pure substances, incompressible substances, and ideal gases. And we'll be looking into a special class of idealized process, which is known as isentropic process. And we'll develop the property relationship for these processes, specifically the TDS relationships or the Gibbs energy relationships. Uh, we'll try to look into reversible steady flow work relationships, the isentropic efficiencies, and the energy balance for various systems. Starting with the Clausius inequality. You know the efficiency of a Carnot engine. Carnot engine is the engine that has the maximum efficiency. And the Carnot efficiency is essentially defined by 1 minus TL over TH. This is how you define the Carnot efficiency. Thermal efficiency is essentially defined by work net out over QH, or you can also define it as QH minus QL over QH, or this could also be written as 1 minus QL over QH. Now, if your engine is having the maximum efficiency, which is that of Carnot efficiency, so your thermal efficiency would essentially be equal to the Carnot efficiency. That means that work net over QH would be equal to 1 minus TL over TH, or in other words, you could say that 1 minus QL over QH would essentially be equal to 1 minus TL over TH. Is this point clear to you?
Yes, sir.
All right. Now, if I if I see I can cancel out this one, this minus sign would cancel out. I can bring TL to this side and similarly QH to this side. This means I would have QL over TL e equals to QH over TH. Is it clear? Is this understandable?
Yes,
Yes,
sir.
sir.
All right. When we are talking about this reversible heat engine, which is a Carnot heat engine, QL over TL, basically both of them are referring to the low temperature reservoir. It is the interaction of heat with the low temperature reservoir. And when we are talking about QH over TH, it is essentially the interaction of heat with regards to high temperature reservoir. So far, is this thing clear?
Yes, sir.
All right. Uh, I can write, all right, before that. So I can say that as my engine undergoes a cycle, as my engine is undergoing a cycle, one complete cycle, what are the heat interactions that are taking? Come on, as my engine,
Uh,
GG.
sir, QH will be converted into QNet and QL.
Just tell me what are the heat interactions that are taking place, specifically, individually. First one, QH coming from the reservoir, which is at TH. Clear?
Yes, sir.
The second interaction is QL that is moving out at a temperature which is TL. Clear?
Yes, sir.
Is there any other heat interaction taking place for this one cycle when I'm talking about one cycle?
No, sir.
All right. Now, if I want to add up all the interactions, add up all the heat interactions that are taking place that are taking place at their respective temperatures for one cycle. So can I write it as this QH over TH minus QL over TL? Can I write it in this form? This is the expression.
Yes, sir.
So it means that all the heat interactions QH over TH minus QL over TL, these are the heat interactions taking place at the respective temperatures. If I look at this expression or this expression, I can write it in this way for a reversible cycle. QH over TH minus QL over TL is equal to 0. Clear? Is this understandable?
Yes, sir.
Yes, sir.
Or if I want to get rid of the signs and I want to write a generic expression, I can write it in this way, that the for a cycle, this symbol represents cycle, the integral or the addition of heats with regards to their respective temperatures is essentially equal to 0. Is it clear? Is this point clear to you?
Yes, sir.
So this is valid for a reversible cycle, that the cyclic integral of heat additions with regard to their temperature is essentially equal to 0 for a reversible cycle. Does this make sense?
Yes, sir.
Great. Now let's look at an irreversible cycle. For an irreversible cycle, I would say the efficiency would be less than that of Carnot cycle. We'll have the same expression, but now we have a less than sign for an irreversible cycle, which means that essentially 1 minus QL over QH is less than 1 minus TL over TH for an irreversible cycle. Again, bringing the same expression, rather than having an equal to sign, I'll have a less than sign for an irreversible cycle. Clear enough? The same expression.
Yes, sir.
That means for an irreversible cycle, the integral of heat additions with regards to their respective temperatures would essentially be less than 0. Clear?
Yes, sir.
Combining the expression that we get for a reversible and irreversible cycle, we form the Clausius inequality, which says for a cyclic process, the integral of heat additions with regard to their respective temperature is less than equal to 0, where the equality sign is for reversible or for the least matter in internally reversible cycle, and the inequality sign is for the irreversible cycle. Clear enough?
जी सर.
Yes, sir.
All right. Now we are considering only, will now consider only the sign where something is, let's say dx or dy, whatever, is equal to 0. We are considering the equality part. Now let's say I have two states. One is where I have volume V1, other is where I have volume V2. Volume is a state function, is it or not? Volume is a state function. Let's say if I go from 1 to 2 and then I come back from 2 to 1. So I have completed a whole cycle. For this whole cycle, the change in volume would be what?
0, sir.
0. Which means that whenever we have the cyclic integral of any change equal to 0 or anything equal to 0, any expression within cyclic integral is equal to 0, that expression is essentially a state function, or it's a property, like volume is a property. Clear enough?
Yes, sir.
This essentially means that del Q over T, when it is equal to 0, this expression basically represents some change in property or change in a state function. Clear enough? Is this point clear to you?
Yes, sir.
All right. Just like I said that dV cyclic integral is equal to 0, so volume is a property. A quantity whose cyclic integral is 0 is a property, for example, volume. Just like that, the del Q over T for a reversible or internally reversible process is equal to 0, cyclic integral of this thing. So we define this thing with change in entropy, and entropy is basically defined as a property. So entropy is a property, and del Q over T for an internally reversible process is defining change in entropy. Clear enough? Is this clear?
Yes, sir.
All right. Now remember that when we are talking about ds, we means S2 minus S1. The change, we are not focused about how we got from 1 to 2. We are only focused about S2 and S1, the values at these two states, and we are expressing ds as the change in the values of S2 and S1. Anyways, so the entropy change of a pure substance can be obtained by making it go through an internally reversible process and then using the equation below that we have seen in the last slide. But this ds is expressed as S2 minus S1. But you need to have, in order to integrate, you need to have a relationship between heat and temperature, which is often not available. Therefore, the tabulated values are used to find the entropy at any state. For instance, if you look at water, which is a pure substance, you can find the properties for entropy under the entropy column for specific states. States are being defined by two independent properties. One could be temperature, the other could be pressure. These two could define your state, and you could find the specific value for that state. What is the entropy value for that state for a pure substance? Now let us look at an cycle, one part of the cycle, this cycle where it goes from 1 to 2 and 2 to 1. The second half of the cycle, while it's coming back, is known that it's an internally reversible process. This is known to me, that it's an internally reversible process. Path 1 to 2, it is not yet known whether it is reversible or irreversible. In such a case, if I have to express the this expression for the cycle, I can say that 1 to 2, going from 1 to 2, del q over t is there, but internally reversible is not written. That means I'm not sure whether it is reversible or not. But for 2 to 1, I know it's an internally reversible process, and I have written internally reversible. And the summation for both the cycles is essentially less than equal to 0. Is it clear so far?
Yes, sir.
All right. Now, since it's an internally reversible process, can I represent the process 2 to 1 as ds or S1 minus S2? Can I represent it with this expression?
Yes, sir.
S1, this is S1, this is S2. So S1 minus S2. I can represent this expression as S1 minus S2. So far clear?
Yes,
The
sir.
second expression. All right. Now, if I take these two on the other hand side, I would essentially have S2 minus S1 is greater than equal to integral of 1 to 2 del q over t. Clear enough?
Yes, sir.
All right. Let's suppose that S2 minus S1 is representing what? Change in entropy as I go from 2 to 1, 1 to 2. As I go from 1 to 2, S2 minus S1 is represented by this expression. Clear?
Yes, sir.
Now, let's say if this process is a reversible process. So this expression would change how? S2 minus S1 should be equal to 1 to 2 del Q over T internally reversible process. Clear?
Yes, sir.
But if it is not a reversible process, that means S2 minus S1, the change in entropy for the process should be greater than this expression. Clear? Or I can write it in this way that S2 minus S1 would be equal to 1 to 2 del Q over T internally reversible process, that the change in entropy for an internally reversible process plus some constant. Clear? If it is irreversible process. Is this
Yes, sir.
point
Yes, sir.
making sense to you?
Yes, sir.
Which essentially means that for an irreversible process, the change in entropy is some value greater than the change in entropy for a reversible process. Got the point?
Yes, sir.
Now, this value which is greater, which is expressed over here as some constant and which is greater than that for the reversible process, you call this as entropy generation. That means the change in entropy for an irreversible process is some value greater than the reversible value, which is entropy generation. This value is a positive value. That means some entropy is generated due to the irreversible process. In other words, you say that some entropy is generated or created during an irreversible process, and this generation is entirely due to irreversibilities. The higher the value of entropy generation, the lower would be your efficiency. The higher would be your irreversibilities, and the lower would be your efficiency. Does this make sense to you?
Yes, sir.
All right. So always remember entropy generation is a positive value. It could either be zero. When would it be zero?
Sir, for reversible processes.
For a reversible process. Very good. And for an irreversible process, it would always be positive. So I'll stop over here and we'll continue with the entropy generation point in the class that we have scheduled for tomorrow.